Hi Year 12s, today we're going to start off by looking at the laws of thermodynamics to give you a bit of a background and the definition of internal energy. First of all, we're going to go through a few terminology notes. So here are some things that you should keep in mind throughout the entirety of this topic. Thermal energy and heat are the same thing. When you're explaining something, you can literally replace heat with thermal energy and vice versa. Some definitions prefer you to use heat or prefer you to use thermal energy or prefer you to just use the word energy. Make sure you learn the definitions exactly as they're given to you because those are the ones that your exam prefers. We can call this heat, we can call this thermal energy, but don't call it heat energy. That's just a bit silly, really. And be really careful that thermal energy and heat are not the same as temperature. So don't confuse heat, which is in energy, units of joules, with temperature, which is units of Kelvin. There are lots of ways that heat and temperature are linked, but we definitely don't want to make them synonymous in our brain. You probably want something to this effect in your notes, so thermal and energy and heat are the same thing, but that's not the same thing as temperature. If the unit discrepancy there between heat and temperature helps you out, make sure you include that as well. Another bit of terminology, never ever ever use the word cold in your answer. You cannot transfer coldness. If you're using cold, you've probably missaid something. Cold, like dark and quiet, is not a thing, but rather the absence of something. Quiet is the absence of sound. Dark is the absence of light. Cold is the absence of heat. Sorry about the overlap there from the PowerPoint. It didn't import into the movie making program very well. But when we talk about, if you want to talk about cold, don't talk about the cold. Always explain and discuss things in terms of where the heat is. Now, oftentimes students struggle to do this because they're really fixated on something being cold. So always go back and think of the heat, and here are some synonyms to give you a hand. If you're talking about an item losing heat, you can say that it's transferring thermal energy away from the system or out of the system. You could say that it's emitting thermal energy to the surroundings. You can say that heat is being removed. And if you're talking about a system gaining heat, you can say that it's absorbing thermal energy from the surroundings. So whatever's happening, whether it's cooling down or heating up, always talk about it in terms of where the heat is going. It's transferring heat away, or it's absorbing heat, it's gaining heat. For your notes, you probably want some sort of note to yourself, never to use the word cold or coldness. Don't talk about the coldness. Always explain and discuss things in terms of where the heat is. If you want to write down some of these synonyms to give you a hand for when you're going back and trying to explain things, that would be good. If you're like, no, I can grasp that from the previous stuff, that's fine too. And a couple keywords and phrases before we really get into the meat of things. I know we've already used system. So a system is a collection of objects. It could be any object you'd like it to be, whatever you're talking about. It could be, the water inside your cup of tea. It could be the actual cup and the tea inside it. It could be the cup and the tea and the coaster that it's sitting on, whatever you decide for your collection of objects. Thermal equilibrium is a little bit harder of a concept to grasp. If two things are in thermal equilibrium, it means that no energy is being transferred between those two systems. Now, a good example is if I've got my coffee mug and it's sat out there all day, it's going to come to thermal equilibrium with the room that it's in. And for my coffee sitting out on my desk, that means that it's going to end up at room temperature. It'll be the same temperature as the room. Now, thermal equilibrium doesn't always mean the same temperature because we could have different pressures and volumes at play. In which case, you might have two things that are at thermal equilibrium that aren't at the same temperature, but they're at thermal equilibrium because no energy is being transferred between those two systems. Now, in the case of A levels, we won't really delve into that. It'll mostly just be, two things at the same temperature. But as you go on to higher education, that will be a distinction that you really have to make. So we're going to go through the 4 laws of thermodynamics and talk a little bit about them so we've got a good grasp of thermodynamics as a topic. Now, in terms of your A levels, you only need to know one of the laws, and we'll spend more time on this law, obviously. But it's nice to know where the other ones fit in, especially if you want to do some extra reading around the area, or if that's something that you're interested in and want to go into that into university. It's nice to have that background knowledge. So historically, the zeroth law was accepted after the first and second laws, but it's more fundamental than either of those. So we didn't call it the third law. We went back and went, actually, this one's, we didn't really call it a lot earlier, but this one's a lot more important. So we're going to call it the zeroth law. It comes before the first. And the zeroth law states that if two systems are both in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. Now remember, a system is just a collection of objects, and thermal equilibrium means that no energy is transferred. Now, at first that seems a little bit oddly phrased, but essentially that's like saying, say we've got three systems. We've got A, B, and C. And so we take a look just at system A and C to start, and they're in thermal equilibrium with each other. So we've connected A and C together, but between A and C there's no heat transfer, there's no energy transfer. And then we decide to do the same thing with system B and C. So we connect system B to C, and when they're connected, there's no energy transfer, there's no heat transfer in between the two of them. So what the zeroth law says, if we've got a situation like this, so we could connect A and C and there wouldn't be any heat transfer, we could connect B and C and there wouldn't be any heat transfer. In this specific case, then if we connected A and B, there wouldn't be any heat transfer. Now, I know you might be sitting there going, well, duh, but that's actually quite a key axiom, that it's based off heat transfer, not temperature, and that we can treat things like that. So if A equals C and C equals B, then A equals B. And even maths has axioms like this built into it that you don't really get into until you go on to a higher level. In essence, the first law is simply energy conservation. The internal energy of a system is increased when energy is transferred to it by heating or when work is done on it. And the opposite of that is also true. The internal energy of a system is decreased when the energy is transferred away from it or when it does work on the surroundings. This is the first law, and your exam does expect you to use this, but it doesn't actually ask you for this as a definition, so you don't need to know this by words. If you want to put the words into your notes, you're more than welcome to, but it specifically asks you to do this mathematically, which we'll take a look at in a moment. Before we take a look at that, what is this term, internal energy? What does that mean? Internal energy is the sum of the randomly distributed kinetic energies and potential energies of the particles in a body. Now, on its own, that sounds quite weird. You might have seen a graph that looks sort of like this. Depending on which exam board you did at GCSE, you might have seen this graph. And this just shows us the number of particles with a particular kinetic energy. And now if you've got sort of this graph here with this lower temperature, this is the explanation for why you can get evaporation without boiling. If you've got a lower temperature, this would be like the random distribution of the kinetic energies. Not all of the inside your water, not all of the particles would be traveling at the same speed. Some are really, really slow over here. Most of them are about whatever this kinetic energy is, and some are quite fast. At a higher temperature, this distribution flattens out so that we've got more higher kinetic energy particles and fewer lower kinetic energy particles, and that peak of kinetic energy shifts to the higher kinetic energy. And now this shaded bit over here, this E min, is the minimum amount of energy required to leave the surface of the liquid, and that's where you get evaporation. So those particles will evaporate, which can happen at a lower temperature than the boiling point. So our internal energy definition relates back to the fact that we've got randomly distributed kinetic energies. So there's a whole bunch of different energies inside that solid, liquid, gas, whatever it is. And it also relates back to the potential energies of the particles. Remember, that depends on their bonds. So if we were to sum this up, the internal energy is equal to kinetic energy of all particles plus potential energy due to bonds. This is a definition that your exam can ask you. This is definitely something that you want to get into your notes so that you've got the definition of internal energy. So I want you to take a moment and pause the video, try to answer the question, either inside your notes or on a scrap piece of paper. In which state do particles have the highest kinetic energy? And in which state do particles have the highest potential energy? Pause the video now. So remember, our solids are just vibrating about fixed positions. Our liquids are, a little bit more free to move around. They can slide past their neighbours, and gases move rapidly and randomly. So as we go solid, liquid, gas, we're increasing the kinetic energy. Our particles are moving faster. As we go solid, liquid, gas, we're also increasing the potential energy. Our particles have the potential to make bonds. The solid particles already have very strong bonds with their neighbouring particles. The liquid particles have strong bonds with their neighbouring particles. The gas particles have negligible bonds with their neighbouring particles, so they have more potential to make bonds. They have a higher potential energy. To increase the internal energy of a system, we can either increase the average kinetic energy of the particles. This will go into increasing the temperature. Or increase the potential energy of the particles. This goes into changing the state. But what can we physically do to increase the internal energy? Pause the video now and give that question a try. Hopefully you've said heat the system, so add thermal energy in some way. That's sort of the key thing that we could do. The other one is more linked with just gases, is to do work on the system. And we will have a better look at this when we get to the gases section of the thermal topic. So the first law of thermodynamics is written mathematically as delta U equals Q minus W, where delta U is the change in internal energy, Q is the heat or the thermal energy added to the system, and W is the work done by the system. Really, this is just saying energy is conserved, right? If we take all of the heat that we've added into the system and take away from that all of the work that the system's done on the outside, then what's left over has to be the change in the internal energy of the system. It's just energy conservation. That being said, this is something that you do need to know. You need to be able to use this in your exam. Now, this specific equation isn't given, but it is just energy conservation. That being said, whatever way works best for you to remember it, whether it's by remembering energy conservation applies to our thermal topic, or by remembering that formula, completely up to you. Now, if you are doing reading around the subject area, you'll see that chemistry is really silly sometimes. They've actually gotten it mixed up in loads of chemistry books, and they've put delta U is equal to Q plus W. That's supposed to be a minus sign, really, but theirs isn't incorrect, but the physics one isn't incorrect. So where's that discrepancy? That actually comes from how we define things. So chemists, like us physicists, define delta U as the change in internal energy, and they define Q as the heat or the thermal energy added to the system. But our definitions of W are different. The physics definition is that W is the work done by the system, and the chemistry definition is the work done on the system. And this gives rise to the negative sign that disappears, so to speak, when you use the chemistry definition. So the only difference is the definition in W. As long as you think of conservation of energy, you'll be all right. But in terms of higher education, if you're going off and doing chemistry, you might want to write it as delta U equals Q plus W, as silly as chemists are. If you're going off and doing physics, you probably want to use it as a minus W. But really, end of the day, it's just conservation of energy. Your exam doesn't expect to see this in a particular way. You can use the positive W or the negative W, whichever definition you'd like, as long as you've got your sign convention correct for your definition of W. So the first law of thermodynamics states energy conservation, and essentially that's like saying the best you can do energy-wise is break even. So any sort of perpetual motion machines of the first kind, you can look up, there's two different kinds, are impossible. We can't have those type of perpetual motion machines. The second law brings in something called entropy, which you don't need to know for your exam, but if you are thinking about going on and doing a future career in physics or engineering, I would definitely look into entropy. It's a really good place to start looking for extra material. And the second law is the casino rule. You can't even break even. This law confirms that perpetual motion machines of the second kind are impossible, so we can't possibly have perpetual motion machines. Sorry to anyone thinking we could have free and unlimited energy. The second law links the concept of entropy, heat, and temperature. The third law takes it a little bit further. The third law links entropy and the temperature with the actual arrangement of particles in the system. If you've done anything in your math class with statistical analysis or counting different permutations of particles, like how many ways can you line up these coins in a different order, this is where that comes in ridiculously useful, and you do loads of it. This is a fantastic place if you want to go and do something above and beyond the syllabus or the specification, to take a look into entropy, specifically with its relation to the second and third law in particular, if your math skills are really good with regards to statistical analysis and counting permutations, counting mathematically and not actually counting, because that would take a really long time with the third law. So we're just going to recap the key concepts and what you need to know for your exam. Heat and thermal energy are the same thing, and that's not the same thing as temperature. In explanations, talk about where the heat goes. Cold, coldness, they're taboo words, don't use them. A system is a collection of objects. If two things are in thermal equilibrium, that means that there's no heat transferred between them. The internal energy of a system is the sum of the randomly distributed kinetic energies and potential energies of the particles in the system. In the first law of thermodynamics, the internal energy of a system is increased when energy is transferred to it by heating or when work is done on it. Remember that this equation is not given in your exam, but it's essentially energy conservation. That delta U is the change in internal energy, Q is the heat added to the system, and W is the work done by the system. Just conservation of energy for the system. And that's everything that you need to know about the laws of thermodynamics and internal energy for your exam. Have a fantastic day.